Welcome to the nuclear chemistry review. The test is going to be multiple choice and short answer. It's actually a very short test, and so you need to make sure that you study really hard because I think there's only a total of 25 questions, and so you're going to really need to know it. It's actually a pretty easy test. If you will study your notes, the review, and any worksheets, everything is straight off of there, just like always. And even though I tell you all that, sometimes y'all just look over the review. Please study the notes as well. All right, so let's get started. Well, this problem wasn't on your review, but I want to make sure we understand that because some of you are still struggling with the numbers when you have them written in a symbol. Remember, the top number is your mass number. I color-coded that in blue. And then the bottom number is your atomic number. And remember, an atomic number is the number of protons, and that's always how we identify an element. And so remember, the atomic number is on the periodic table. We can find that. It's usually the big whole number. But the mass number is not on the periodic table. And that is something that tripped some of you guys up on and gals on the last test, as you couldn't find the mass number on there, and you forgot that what's on the periodic table is the average atomic mass of all the isotopes. But the mass number is for a specific isotope. In this case, we would call this xenon 132. And of course we can write it like it's shown here, but remember we can also say xenon 132 like this, and that's telling you the mass number. Okay, so let's just do a quick electron, proton, and neutron count for this. Of course, if our our atomic number is 54, that means that we have 54 protons, and then because this is a neutral atom, we would also have 54 electrons. And then the way that we find the neutrons is to subtract the atomic number from the mass number. So we would do 132 minus 54, and we would get 78 total neutrons. And so that's how you do that. So if you did not understand how to do that on the last test, you need to know how to do that again. So make sure you practice that if you want to go look at some old worksheets from Chapter 3 or your notes from Chapter 3. So let's move on to the first question that's on the review. All right, so this problem actually had a mistake, so go ahead and fix that in the problem. It gave you gold 79, and it should have been gold 202. They inadvertently put the atomic number instead of the mass number. So go ahead and make that change, and then we can go ahead and balance this. Remember, when we are balancing nuclear equations, we need the mass number to be the same on both sides, and we need the atomic number to be the same on both sides. So in order to do that, we'll see that we're going to do this, and it says you may use alpha particles, beta particles, positrons, or protons. So first things we're going to do is go ahead and put a plus sign, and we know that we have 202 on the product side and we have 206. So we're going to put a 4, okay, and then we're going to see where we have 79 and we have 82, and so we're going to put we're going to go ahead and put a helium particle because we know that alpha decay is possible, and so we're going to put that helium particle. But if we notice this only adds up to 81 on the reactant side, and we need 82. So this one would also, in addition to this, require a positron particle. And remember, a positron is basically a positive electron, so we would do that E, and we would do 1 and 0. Remember, we could also use the beta sign, but it would still be a positron particle when we write it like that. And so now everything should be balanced. So question number 2 is just asking you to define the following terms. And I would like to add these 4 terms to that as well. Make sure that you're studying this either in your book, look them up, or some of these were in our notes. You were supposed to do your vocab for Parker points, so hopefully you did that and you already have them. But make sure you know these terms. This test is heavy on definitions, and these should be easy points that you should be able to take and run, because if you know the definition, you should be able to answer the question. So make sure you're studying the vocab. So number 3 wants you to write the complete nuclear equations for the following reactions. So the first one is molybdenum 91 is undergoing positron emission, And if you recall from positron emission, that means we basically have a positive electron. So we're going to do E and then 0 at the top. And then what's going to be left is we have to have our atomic number add up. So we need to figure out what plus 1 is going to equal 42. And of course that's going to be 41. So we'll write 41 on the bottom. And then of course the atomic number does change, but the mass number does not change. And so it's going to be 91 on the top. And if we look that up on our periodic table, we'll see that that is NB. And so now we would double check that and it would be balanced. The next one is a beta decay. Have a helium-6 undergoing beta decay. And beta is a negative. So it's a negative electron. So it's going to look like this, -1 and 0. And then we see what's going to be left. And so of course we have to see what plus -1 would equal 2. So that's going to be 3. Doesn't change on the top, so it stays as 6. And when we look up element with an atomic number of 3, we see that that is lithium. And so now that one would be balanced. And then C is polonium undergoing alpha decay. And remember, whenever you see alpha decay, that is a helium particle, but it's a helium-4 particle, so 4 and 2. And then we see what we have to make it be so that it could equal to 84, and that would be 82. And then we would have 190 on the top. And when we look at that, we see that we have Pb for lead. And then the last one is electron capture. And the difference between electron capture and beta decay is that the electron is now going to go on the reactant side because the nucleus is taking in. And so now we simply add those up and we would get 54 on this side for the atomic number. And then the mass number stays the same. And then we look up 54 and we see that that is xenon. And so you have to know how to do all 4 types on the test. So make sure you practice that and look over some of the worksheets we had that had the different balanced nuclear equations in there. Question 4 says, what are 3 ways of detecting radiation? And explain how each one works. Well, first of all, let's look at the film badges. And we talked about that one when we did one of our journal questions. And we said that film badges detect radiation in people. So that's what we need to worry about there. In people is the big key there. It actually has film that darkens when exposed to radiation. Geiger-Müller counters count the electric pulses carried by gases. So they count electric pulses. That's going to be what's your clue word there. And whenever you've seen movies or anything where they're detecting radiation and you hear that real click, 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 click or whatever when they're waving a wand in front of an item, that's what a Geiger-Müller counter is. And then the scintillation counters are counting scintillating light, and it converts it into electric signals, and that's how they detect radiation. Those, again, are some of our vocab or definitions. You need to make sure you know the 3 types. Film badges, Geiger-Müller counters, and scintillation counters. You also need to know the difference between fusion and fission. And if you kind of look at their base words, it's kind of easy to figure out. Fusion is combining 2 lighter nuclei into a heavier nuclei, so 2 lighter ones into a heavier one. Example of a fusion reaction is the sun. It takes 2 hydrogen nuclei and combines them into a helium. And then fission splits the atom. Okay, it takes a heavy nuclei and splits it into 2 lighter. So they're opposite of each other. What we are doing at nuclear power plants is nuclear fission, so we're splitting the atom. If you were to see this in an equation, you would want to look for those key words as far as the atomic number. So in fusion, you would see 2 smaller atomic numbers on the reactant side, and then on the product side, you would see a heavier atomic number atom. And then, of course, fission would be the opposite. You would see a heavier atomic number, and then you would see some neutrons being added to it. And then on the other side, it would be a lighter, 2 lighter nuclei with some leftover electrons because they are involved in that chain reaction. So make sure you know the difference between fission and fusion. So some more of the definitions. This was from our flipped lesson, but once again, it's straight out of the notes and it's straight out of definitions. You need to know the three main parts of a nuclear reactor. The shielding is what contains the radiation. We talked about that when you see the big, huge domes of concrete. That is for shielding. It's to contain or absorb any stray radiation from the nuclear reactor. The control rods are the rods that they are lowering and raising, and they are absorbing the excess neutrons, because remember, a chain reaction produces the reactant for the next part of the reaction, and so we have to control and absorb some of those neutrons so that there's not too many neutrons bombarding other atoms. And then the moderator slows down the neutrons. So it's not absorbing them, it's just slowing them down so they're not moving so fast so that they can't bombard the other atoms with as much force because they've been slowed down. Alright, so gold 198 has a half-life of 2.7 days. How much of a 96-gram sample of gold will be left after 8.1 days? So this is a half-life problem, obviously, so this is where we set up our chart. I've started the chart for you, amount versus time elapsed, and so we're just going to start going through our half-lives and see how much is left. So after one half-life, which would be 2.7 days, we would have 48 grams left, and then we keep going. So after an additional half-life, which would be 5.4 days, remember we're just adding 2.7 each time to get to the next half-life, we would have 24 grams, and then we add another 2.7 days and we get to the 8.1 days that it's asking about, and so we do half of that and it would be 12 grams. So in fact 12 grams would be our answer. After 8.1 days, we would have 12 grams of this sample left. And I think our next one is our half-life, and then we're done with this review. Same thing, this time we have a half-life of 8 days, and we want to determine how many days will elapse for our sample to go from 0.80 milligrams to 0.1 milligrams. So this time we're going to work at the opposite. We're going to decay it to 0.1 and see how many days that takes. So after one half-life, we would go to 0.04 milligrams, and of course that would be 8 days that passed. We decay it another half-life, and we'd go to 0.2 milligrams, and of course that would be 16 days. And then we go to the 0.1, which is what it's asking for. It asks for how many days, and we add an additional 8 days, so our answer here would be 24 days. And so we're going to box that and say that that's our answer. It would take 24 days for a sample of the indium-131 to go from 0.8 milligrams to 0.1 milligrams. It went through a total of 3 half-lives, 1 here, 2 here, and a third. So it took 3 half-lives, which was a total of 24 days. All right, that is the end of our video lesson. Be sure to study your notes, your vocab. I can't stress you enough. This is a very heavy vocab test. So study all those vocabs that we had you write for Parker Points, and look over your notes. Also, make sure you look over those journal questions. Sometimes those can help you on a test as well. I will see you in class.